Thank you. Good morning, everybody, and thank you for attending to my PhD presentation session. My name is Nima Asgari, and I'm going to present my PhD research on agrivoltaic food production systems for cold climates, with a special focus on techno-economic feasibility assessment of sustainable and renewable solutions with heat pump integrated greenhouses, as well as near zero vertical agritunnels. And I'm privileged to have this work supervised by Dr. Joshua Pierce. And I'm also grateful to have Dr. Michelson, Dr. Tang, Dr. Sherrod, and Dr. Ali Abadi as my committee members. I would like to start with a short review on the critical global crisis of population growth, energy demand growth, and global warming. In the last 23 years, the population of the world has increased from 6.2 billion to 8.1 billion, which is a huge number. And as a result of that, in the last 10 years, the energy demand worldwide has increased from more than 350 exajoules to 400 exajoules almost, even though the contributions of renewable energies had an improvement by 56%, but on the other hand, the fossil fuel consumption also had a rise by 13%, and which in turn has introduced the accumulative greenhouse gas emissions in the highest level in the recent years, thereby increasing the temperature deviations of mean global temperature deviations from the baseline to the critical level of 1.2 degrees. If we want to address these crises and challenges, especially in food and energy sector, sustainability and renewability would be the best combination, which can enable us to provide the food and energy requirements of that high-level population while reducing the carbon footprint of a conventional food and energy technologies. To be more specific, in my thesis, three technologies in food and energy sector that are kind of modern and sustainable and renewable based can help us to address these challenges, and specifically controlled environment agriculture, in short CEA, solar photovoltaics, as well as heat pumps, which can outperform their own alternatives or conventional forms. Starting with CEA, it has higher year-round productivity and low water consumption, higher biodiversity and controllability on the microclimate. And compared to the conventional form of farming, and solar PVs are the most affordable and the fastest growing renewable energy technology, and it is completely easy to implement compared to the other technologies. And heat pumps are fully electrified with high coefficient of performance values compared to the conventional energy provision systems. The combination of these three technologies will result in sustainable agrivoltaics for CEA. What is the agrivoltaics? Agrivoltaics is the co-development of solar photovoltaics and agricultural lands, and it can address the land use challenge of photovoltaic technology by sharing the same piece of land for both crop production as well as electricity generation. And it has different forms depending on the landscape restrictions and farming operations. But in our thesis, our main focus is on the indoor agrivoltaic or agrivoltaic for a CEA, and this is the sample picture of its application. According to the existing research in the literature, we have identified some limitations in this field, and the most important of them are reported here. And there is a lack of transparent and scalable models for both CEA itself and the integrated technologies. Most of the existing models are either complex simulations or some simplified basic assumptions on case studies rather than being scalable models for more generic applications. There is a lack of comprehensive techno-economic models, especially on the indoor vertical farms, incorporating all economic aspects of the agrivoltaic projects. There is no studies on agrivoltaic CEA in Canada, except for the ones that we have done in our research group, and all of the other worldwide research are mainly on Mediterranean, continental, and oceanic climates rather than subarctic and similar to Canadian climates. And the studies are either on agronomy or focused on the energy and technical feasibility. And the combination of these two and in the existing research is limited. And there is also a limited number of experimental semi-transparent PV modules. Separately, a wide range of these PV modules is tested, but in one single study, one single location, and one single cultivar, the number of the varieties is limited. And among the research, the number of indoor vertical farms that are powered by agrivoltaics is also limited. Based on the existing research gap, so we have proposed five objectives for our research, including development of integrated energy modeling framework for CEA, heat pumps, HVAC system, and solar photovoltaics, and assessment of electrified and renewable power food production systems in Canada, and application evaluation of semi-transparent PV modules at the food energy interface, and economic and environmental analysis of agrivoltaic CEA, as well as system level and crop level optimization of indoor agriculture. Our thesis have been divided into two sections. First section is on agrivoltaic greenhouses, and the second section is focused on agrivoltaic indoor vertical farms, or more specifically agrotunnels. Each of these sections have three separate chapters. So in total, we have 6 core chapters for the thesis. And for the first section, one of the papers has been published and the other 2 are under review. And similarly, for the second section, the agrotunnel section, again, we have 1 published paper and 2 others under review. So we start with agrivoltaic greenhouses. We had conducted feasibility experiments on growing spicy pepper and cherry tomato plants under agrivoltaic treatments at Wide Research Center of Western University in Ilderton. We had 36 samples for either of these cultivars that were placed in 2 identical greenhouses, as you see in this picture. And the cultivation period was 18 to 19 weeks from April to August. For each agrivoltaic treatment, we had a table on top of which the semi-transparent PV module was placed, and underneath the plants were growing. And 6 agrivoltaic treatments and 6 PV treatments were categorized in 3 groups of pattern silicon modules with 44% and 69% transparency, thin film modules with 50% transparency, and blue and red color filtration, and pattern luminescent solar concentrator with silicon cells and 69% and 53% transparency and red color spectral filtration. And the measured parameters included hourly temperature and relative humidity of greenhouse, as well as outdoor, peak day, spatial and temporal PAR maps, and weekly gross metrics of leaf chlorophyll content, plant height, and yield values. So we also developed the scalable thermodynamic heat pump model using Python based on the thermodynamic principles. And we had 2 models of air source and ground source heat pumps. And for the ground source heat pump, we had 2 modes of with a horizontal heat exchanger and a vertical heat exchanger for further comparison. We also had a thermal model for our greenhouse that was developed in Python as well, based on the global heat balance equation, incorporating the heat sources as well as heat sinks in the hourly quasi-steady state mode. We also had another advanced thermal electrical model for a fixed size this time, greenhouse using open source Energy Plus and OpenStudio, and we use the capabilities of Energy Plus to kind of have more controllability on set points and schedules. In addition to all of these models, we had a load management HVAC system to kind of simulate and manage the performance of other HVAC equipment like ventilation fans, circulating fans, humidifiers, dehumidifiers. And we had three scenarios, as you see in this text box and this picture. The first one was conventional gas-heated greenhouses, including the natural gas grid, gas system generator, gas heater, and in conventional AC or chiller. Modern heat pump-based greenhouses, in which these equipment were replaced with heat pump and electric steam generator, and agrivoltaic heat pump-based greenhouses, which was similar to the heat pump, the second scenario, but with additional rooftop integrated solar PV system. And at the end, we used open source SAM software to simulate the generation of our PV system as well as to evaluate the financials of our agrivoltaic system. We see these are some beautiful pictures of our healthy plants that were grown under agrivoltaic treatments as well as the control section. So for all of the plants, we could successfully grow them and harvest their fruits without any specific problem. We would like to start with the temporal and spatial distributions of PPFD values across the treatments as well as the control. Figure 1, we see the spatial variations. It is the top view of our greenhouses, greenhouse 1 with 4 treatment areas and greenhouse 2 with 2 treatment plus control section. And these heat map colored numbers are representing the received par values on plant height under the treatments and in the control section. And we selected an almost 90% sunny day as a representative day on July 12th and half an hour time period, time window from 12:30 to 1 p.m. And as you see, obviously, the received power values in control section is considerably higher than the other treatments. And in the next level, we have this treatment, 53% luminescent module, as well as 69% silicon module. On the other hand, thin film modules with 50% transparencies and color filtrations had the least level of received illumination, at least on that period of time of the day. And so somehow for the remaining treatments, 44% silicon and 69% luminescent, the received power level was kind of in moderate range. And if we look at the temporal variations, we see that there are 2 peak points, which is due to basically a good match between the angle of solar radiation as well as the existing open areas around the treatments. But we also, even for control section, where there was no shading barriers, so we see a kind of decreasing trend and a minimum point coincident with the same minimum point for all other treatments. This is on that period of time, the weather was partially cloudy for a short period of time by checking the solar radiation values. So this is the main reason behind this minimum occurring on the control section. And by looking at the control areas received PPFD, we see that especially for the late afternoon, it's some kind of somehow passes beyond the desired level of PPFD for tomato and pepper crops, which is between 1200 and 1500 maximum. But with the same trend, we see that this treatment, 69% silicon, is following the treatment, but with a lower range of absolute received PPFD values that falls in the desired range of the crops. But the main reason that this is following the trend of control section is that one, it has the maximum transparency among all other treatments, and it is placed on almost the west side, and which is very close, very suitable place to receive the maximum sunlight in the late afternoon without any specific barriers. And it doesn't have a specific spectrum filtration, which is very similar to control condition, but with lower transparency. And the most important parameter, the total fresh harvested weight, is illustrated for both crops, tomato and pepper, across the treatments and control. We see that for all of the treatments for both cultivars, the total harvested yield is more than the yield of crops in the control section. This is the main reason explaining this fact is that we can say the solar photovoltaic modules could play the role of shading screens, which is commonly used in the commercial greenhouses to prevent the excess sunlight from penetrating into greenhouse and increasing the heat and light stress of plants. And at least for this 4 months period, we can say that the solar PVs could play a positive role in kind of a traditional greenhouse and to save the plants from excess light and heat stress. And it didn't it didn't have negative effect on the yield values directly. But since we had to select the most successful semi-transparent PV treatment, so we selected the one with the highest level of significance factor for either of these crops. And in this picture, we see that how high level of heat and light stress can make the plants in the control section sun-scald and dry compared to the relatively healthy plants at the same day and the same moment in the agrivoltaic section. So from now on, we start our simulations, and we selected the tomato greenhouse to do further investigations on that. So we created a 3D model of our hypothetical semi-commercial greenhouse in OpenStudio, following some standard commercial ranges. We consider some areas for open vents on the rooftop of the greenhouses, and the remaining area was covered by selected semi-transparent PV module, 69% silicon module. And as you see, the optimized final rooftop integrated PV on this greenhouse turned out to be 144 kilowatt. So before starting simulations, we need to verify the accuracy of our model's performance. So we compared our heat pump model against the experimental data of a heat pump test center in the US. So we see a good alignment between the simulations and the experimental data. Similarly, for our greenhouse Python model, we see a close agreement between the results of our simulations as well as two other simulation models that were previously validated against experimental data. And for our Energy Plus and Python HVAC model system, we see that the key metrics and key KPIs fall in the range that was reported for commercial greenhouses in Southern Ontario. So here we evaluate the performance of our heat pump and heat pump components. So by looking at figure 7, we see that the total power consumption of the compressor for air source heat pump was considerably higher than that for ground source heat pumps in both heating and cooling modes, and the same level of the demand. This is the main reason that the COP of ground source heat pump is higher than that of air source heat pump. And for the case of London, Ontario, there is only slight difference between the seasonal COP and EER of vertical ground source heat pump and horizontal ground source heat pump. And here we can see how beneficial can be the replacement of conventional energy provision systems with fully electrified heat pump. In scenario 1, we see that the gas heater can provide the heating loads and the AC or chiller can meet the cooling demands. And if we replace these two with a fully electrified heat pump for the same level of heating and cooling load, we will see that the natural consumption will obviously be 0, but instead the electricity consumption will increase. But when the heating load is 2.8 times of the cooling load, by replacing it with heat pump, the annual electricity consumption increases by only 1.6 times. This is due to the high level of COP of heat pump compared to the conventional energy provision system. So here, there is a trade-off between natural gas consumption reduction as well as electricity increment. So we need to do analysis on the economics and the environmental metrics to get a final conclusion. And by looking at figure 9, we see that the annual energy cost is reported for all of the scenarios. For scenario 1, it includes the natural gas cost as well as electricity cost, but for scenario 2 and 3, it is only electricity cost, obviously. By comparing scenario 3 with scenario 2, we see that the agrivoltaic could cover 13% of annual electricity demand, which is equal to 7% drop in electricity cost. And if we compare agrivoltaic greenhouse with conventional greenhouse, we see that if we remove the natural gas heater and replace it with heat pump, and we also integrate the agrivoltaic system, we will increase just the annual electricity energy cost by only 5%, and which is mainly due to the subsidized prices of natural gas compared to high prices of electricity. And if you look at the environmental results, the numbers are even more impressive. So we need to include both direct carbon emission mitigation as well as indirect carbon mitigation. Direct comes from the natural gas consumption, and indirect is due to fossil fuel-based grid electricity, which is equivalent carbon dioxide emission, and which is not considerable, at least in the case of Ontario, Canada. So for the second scenario greenhouse, the carbon emission mitigation is equal to 67.9% compared to the conventional one. And for the agrivoltaic greenhouse, we see that it is equal to 71.7% carbon emission reduction compared to the conventional greenhouse. So if we want to review the contributions of first section, we could develop open source realistic physical models for heat pump performance, as well as thermoelectrical model for greenhouse and the other HVAC equipment. We examined the crop performance under semi-transparent PV systems through experiments. We also showed feasible electrification using STPV heat pump integration. We also proposed a comprehensive framework for food energy co-optimization and in rooftop integrated greenhouses in Canada. There was also some limitations for these sections that need to be to addressed in the future studies. Experiments were limited to a 4-month summer period, so repeatability and year-round performance of crops were not fully examined. So shading from nearby panels, tables, and structures added some variability to light distribution and crop response. The experiments were not done in a fully modern greenhouse with advanced climate control. So, and rooftop operation of PV modules was not tested because of some limitations that we had in the university. So it limited our understanding of PV systems performance data under real conditions. And capital installation and maintenance costs were not included to provide a comprehensive techno-economic analysis on the agrivoltaic greenhouse project. So in the second section, we evaluate the techno-economic details of agrivoltaic indoor vertical farm, or more specifically, agrivoltaic agrotunnel. What is the agrotunnel? Agrotunnel is a fully electrified, climate-resilient indoor farm manufactured by Food Security Structures Canada for distributed applications in northern climates. It is designed for both underground applications and above-grade portable applications that can be powered by agrivoltaics. And it is equipped by heat pump and other HVAC systems, as well as true vertical grow walls with hybrid aeroponic, hydroponic cultivation system. And its pilot version is installed at Wired, where we conducted our experiments, and it has 8 grow walls, as you see in this picture. But its commercial max version has 22 grow walls on the same piece of land. So we ran multiple cycles of experiment on 100 plants of lettuce, Swiss chard, and basil in the pilot agri-tunnel. And this agri-tunnel has 70 LEDs and 8 grow walls. And on each grow wall, there are 720 open ports, as you see in this picture. And the total time period that we ran our experiments was between 9 to 10 months. And the most important data that we collected included current and energy data, PPFD, data, temperature, relative humidity, water consumption, labor time, nutrient consumption, as well as other materials, and total yield of cultivars. We also developed ASHRAE-aligned thermal electrical model for predicting the loads of our agri-tunnel using Python. We incorporated the effect of all of the thermal electrical equipment. And using SAMA, the open source equivalent of Homer Pro software, we size our net meter near zero on-grid PV system across 6 North American locations, including London, Montreal, Edmonton in Canada, Boston, Santa Fe, and San Francisco in the US, that can power the agri-tunnel. And we also developed the comprehensive economic model to incorporate all financial aspects, including capital cost, operation and maintenance cost of a PV system as well as agri-tunnel, and to include the revenue streams, which is coming by selling the mainly products and agricultural products. We also defined some KPIs to evaluate the performance, like cost per plant index, cost per kilogram of harvested fresh weight index, net present cost, net present value, payback period, and return on investment. So here we see the pilot agri-tunnel at wired, and also the clamp meter, which was connected to the main circuit breaker of the agri-tunnel to measure the input electricity as well as the extended electricity toward the other equipment of the agri-tunnel. We see some sample pictures of our cultivation experiments. We had isolated a small section from the main part of the agri-tunnel to run our shorter photoperiod experiments on the plants. We also used PPFD, commercial PPFD sensors and open source sensors to collect the most important data. Again, we needed to verify the performance of our models first. So we compared the performance of our agri-tunnel model against the simulation results of HAP software, as well as the actual measured energy data during 2 months in 2024. We also fitted a curve and surface for the heating and cooling performance of the commercial heat pumps that were installed in the agri-tunnel against the manufacturer's datasheet. At first, we ran a preliminary feasibility analysis on the pilot scale agri-tunnel to evaluate the net zero opportunities for our agrivoltaic system. So as you see in this table, the power rating of the agrivoltaic system ranged from 41 kilowatt for San Francisco to up to 48 kilowatt in Edmonton and London, even though the variations in the climatic conditions of all these locations was considerable, but the changes in the size of the PV system was not that substantial. This is due to the climate resilience feature of the agri-tunnel mainly. And we also studied the variations of land use footprint of PV system against the transparency of PV modules across all locations. Obviously, by increasing the transparency, the total land area required for PV installations increases, but we see a significant gap between the results of the Edmonton and other cities. This is due to the lower angle of solar radiation in Edmonton, which leads to higher inter-row considerations for PV arrays to avoid shading on the back sub-arrays of our PV system. From now on, all the data that we had captured in the pilot scale agri-tunnel, we have extrapolated for commercial scale under controlled temperature, relative humidity, water pH, and electrical conductivity, which is reported for the cultivation of lettuce and Swiss chard in this table. So we started with these experiments to target the high-value cultivar and to evaluate the revenue streams as well as light intensity effect. So here we see the annual yield of commercial agri-ethanol reported for different cultivars or different products. We see the maximum ranges achieved for these three varieties of lettuce. And the next level, we have Black Simpson and Red Salad Babel varieties, as well as Swiss chard. But for the maximum crops, we also have another labeling named Spring Mix. Spring Mix is the green mix of different varieties of lettuce family with high market value because of their organic nature. Even though officially our products are not labeled identified as organic in agriethanol, but due to the agriethanol's capabilities and all the nutrient and microclimate considerations that we had during the cultivation, achieving this level of production is possible for agriethanol. So based on that, in order to target the threshold that the economic viability of agrivoltaic agriethanol can be maintained, so we kind of compare the annual yield of different cultivars across different Canadian market classifications. In this picture, we see that for the selected case 2 and case 3, the organic spring mix production, we could achieve the higher revenue streams for the budget, mid-range, and luxury markets in Ontario with revenue of more than 100,000 USD per year. This level of revenue can possibly kind of maintain the economic viability of agrivoltaic agriethanol. So in order to identify the energy conservation opportunities that are bound with the artificial lighting system in the agriethanol, we check the variations, the possible variations under the limitations that we had in the agriethanol. So in figure 18, we see the PPFD map, which is illustrated for 4 category of walls. Category A and B are representing the walls that were placed in the middle aisles, and C and D are for the walls that are in the side aisles. For category C and D, if we reduce the difference between the distance between the LED lights and the grow walls by 10 centimeter only, the average received PPFD will increase such that by reducing the photo period from 24 hours to 23 hours, so we can maintain the average DLI, which is the most significant for photosynthesis, in almost constant level. So by doing so, we can reduce the PV power rating size by 1.5%, and we can have a drop in levelized cost of electricity by 6.2% and 8.3% reduction in net present cost of the project. And in the next phase, we tested basil as the second cultivar, which was a high-value cultivar. And we also ran photoperiod variation experiments, also evaluating the techno-economic performance of our agrivoltaic agriethanol with basil cultivation. In this table, the variations of annual yield and annual labor against the variations of photoperiod and crop density is evaluated. And obviously, by increasing the crop density, the annual yield increases. But on the other hand, the total time for harvesting more crops will increase, of course. But by decreasing photoperiod from 24-hour to 18-hour, except for some exceptions, generally the annual yield decreases because the resulted DLI with shorter photoperiod becomes lower than the optimized DLI for basil cultivation. And on the other hand, the labor also, the harvesting labor also decreases in 18-hour photoperiod because the plants that are grown under shorter photoperiod are more delicate and more thinner, and their stem is not that thick compared to the 24-hour photoperiod plants. So it is very much easier to harvest and trim them, especially at the end of their cultivation cycle, when we want to remove them and replace them with new seedlings. And from the energy viewpoint, for all the 6 North American locations, we sized our net zero PV system for 24-hour photoperiod and 18-hour photoperiod scenarios. For 18-hour photoperiod, we had 24 cases, each standing for the different start time of a lighting system. So, and the most important metric that we considered in selection of the best scenario was the minimum net present cost or minimum PV size. We also considered the alignment between the photoperiod time or lighting operation time, as well as the working hours of growers, engineers, or other workers in the agrotunnel to provide suitable environment for them. So based on that, the minimum possible PV system for, of course, 18-hour photoperiod was selected for either of these locations. Since there was a contradictory variations and effect of photoperiod change and crop density change on our objective functions like net present cost of PV system and PV system size and annual yield values and annual labor time. So we illustrated the NPV values across all these cases to do a sensitivity and to select the best one in terms of economic performance. So for all locations, we see that the maximum crop density with 24-hour photoperiod has received the maximum net present value, regardless of the positive effect of shorter photoperiods. And this is mainly due to the high effect of organic basal price that can kind of change the outcomes of the story, and it can magnify the economic outcomes of the revenue and yield on the total agrivoltaic agrotunnel project. If we compare the net present values of Canadian cases with American cases, we see that almost for all of the cases and all the cities, the net present value in Canadian agrivoltaic agrotunnel is more than the American ones. And this is due to the high electricity prices in the US, as well as more strict net metering policies and regulations compared to Canada. And this table shows the most important results on the techno-economics of our agrivoltaic agrotunnel project. So PV capital cost and operation cost increases by PV system size directly across different locations. But there's also one other parameter named paid to grid during the lifetime of project, which is 25 years. And this parameter is almost negligible for all Canadian cases as well as Boston in the US, but it is considerable for Santa Fe and San Francisco. And in these two locations, the net billing policy, which is the third version of net energy metering, is applied. And under this policy, the selling price of electricity from PV to the grid is much less than the buying price from the grid, which leads to oversizing the PV to generate more and to compensate for this difference. So in the optimization process actually stops at the point that this oversizing cost, the capital and investment cost of this oversized PV surpass the paid to grid amount. So, but if you look at the levelized cost of electricity metric, even considering this strict conditions in net energy metering, we see that LCOE of grid-tied agrivoltaic is considerably lower than grid-only agrotunnel. So again, we see the positive effect of photovoltaic technology in financial savings of our projects. And here, by looking at ROI and other metrics, we see the success of our agrivoltaic agrotunnel project, the whole project altogether, and the ROI values are substantial for all of the cases, and the DPP, the discounted payback periods are suitably low, ranging from 1.6 years to 2.2 years, and cost per plant and cost per kilogram indices again, are higher for American cases compared to the Canadian ones, which is due to the higher electricity prices as well as higher labor rates compared to Canadian cases. And at the end of this section, the contributions that we had included developing an integrated thermoelectrical model for true vertical farming building and introducing agrivoltaic agritunnel as a sustainable food production solution for cold climates, and examining saving opportunities on lighting energy and labor levels in this indoor farming building, demonstrating the techno-economic feasibility of near zero and net zero energy indoor farms, and evaluating the techno-economic sensitivity of on the North American locations, and linking cultivation strategies with market options and to improve the financial performance, and providing techno-economic optimization framework for net metered agrivoltaic agritunnels or on any other similar indoor farms. And the limitations of this section included the model that we considered was incorporating the plug loads only and did not include safety factors for future load expansions. The analysis focused on grid-tied systems, while the feasibility of off-grid PV system with battery size optimizations could be assessed as well. The light intensity scenarios were not validated through crop and plant growth experiments, and various lighting technologies could be compared to evaluate PPFD photoperiod trade-offs from the energy cost, capital cost, and revenue perspectives, and to select the most optimized one. And there are still lots of research opportunities for future studies, conducting multi-year full-scale rooftop experiments to evaluate seasonal crop responses and long-term productivity in greenhouses is necessary, and performing comprehensive techno-economic optimization on agrivoltaic greenhouses to include the capital cost and operation and maintenance cost and carbon dioxide management and other policy incentives can be useful. Investigating off-grid agrivoltaic systems with optimized battery storage, as well as exploring capital cost reduction pathways for agritunnels and modular construction approaches for scalability, developing intelligent energy management system and control strategies with IoT sensors, and expanding analysis to a broader range like high-calorie cultivars to advance the food security sector, and to conduct life cycle assessments and embodied carbon analysis for environmental evaluations. And that's it. At the end of this journey, I would like to sincerely thank all people that had a supportive, meaningfully supportive contribution into accomplishment of my thesis. I would like to deeply thank Dr. Joshua Pierce. He's an exceptionally supportive supervisor, and he made this opportunity possible for me. And his positive, open-minded approach, his insightful guidance, feedbacks, and his availability shaped this research considerably. And I would like to show my sincere and deepest appreciation to my wife, Sevda, who accompanied me during this journey in Canada. And her support, her sacrifice, patience, love, understanding during this journey made this work possible. And without her encouragement in targeting this position that was offered by Dr. Pierce, maybe there was no such PhD research for me at all. I'm also grateful to my parents, parents-in-law, sister, brothers-in-law, and their encouragement and belief in my academic path have always motivated me. I also have a special thank to my little nephew, who was the youngest member of the agritunnel and helped me a lot during the time that he was here. I'm grateful to my committee members and for their the examination of my thesis. Of course, their comprehensive review and feedbacks and suggestions and advice will be definitely helpful in shaping this research. I'm thankful to all FAST members, especially the ones that I had close collaboration and co-authorship. It is hard to name all of them, but I feel like this picture shows most of them somehow, and their presence created a warm environment for our FAST family. And special thanks to the CEO of Food Security Structures Canada, Kim Parker, as well as previous co-founder of this company and the technical advisor of all of our experiments, Greg Whiteside. They were always available to help me in any matter that they could. And I acknowledge our field station manager, Grant Edwards, and technician, Caroline Rosenberg, and the CEO of Jericho Lab Company, Frederick Gollum, for their hands-on assistance and their technical expertise, as well as support in farming process. And thank you all for your time and attention to my presentation.